Welcome to this thermal physics lesson. In today's video, we're going to explore four key areas of thermal physics: temperature scales, thermal expansion, heat and phase changes, and heat transfer methods. Let's break down each concept step by step so you can understand these fundamental principles. Let's start with temperature and temperature scales. First, what is thermal equilibrium? When two bodies have the same temperature, we say they are in thermal equilibrium. This means that when they're in contact, there's no net heat flow between them. An important principle called the Zeeroth law of thermodynamics states that if system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, then systems A and B must be in thermal equilibrium with each other. Now, let's talk about temperature scales. The Celsius scale is based on the freezing and boiling points of water, which are 0 degrees Celsius and 100 degrees Celsius respectively. The Fahrenheit scale is also based on water, with freezing at 32 degrees Fahrenheit and boiling at 212 degrees Fahrenheit. The Kelvin scale is an absolute scale with 0 at the theoretical temperature where molecular motion stops. This is negative 273.15 degrees Celsius or absolute zero. Here are the conversion equations between these scales. To convert from Celsius to Fahrenheit, multiply by 9/5 and add 32. To convert from Fahrenheit to Celsius, subtract 32 and multiply by 5/9. To convert from Celsius to Kelvin, simply add 273.15. In the gas thermometer scale, the ratio of two temperatures is defined to be equal to the ratio of the corresponding gas pressures. Mathematically, this is expressed as T2 over T1 equals P2 over P1. This relationship is derived from the ideal gas law and is the basis for the absolute temperature scale. Next, let's explore thermal expansion and thermal stress. When a material's temperature changes, it usually expands when heated and contracts when cooled. This is called thermal expansion. For linear expansion, the change in length delta L is proportional to the original length L0 and the change in temperature delta T. Mathematically, this is delta L equals alpha times L0 times delta T, where alpha is the coefficient of linear expansion. Similarly, for volume expansion, the change in volume delta V is proportional to the original volume V0 and the change in temperature delta T. The equation is delta V equals beta times V0 times delta T, where beta is the coefficient of volume expansion. For isotropic solids, beta is approximately equal to 3 times alpha. Now, let's talk about thermal stress. When an object wants to expand or contract due to temperature changes, but is prevented from doing so, it experiences a thermal stress. The stress is given by the equation F over A equals negative Y alpha delta T, where F is the force, A is the cross-sectional area, Y is Young's modulus, and alpha is the coefficient of linear expansion. For example, bridges have expansion joints to prevent thermal stress damage. When a bridge heats up in summer, it needs room to expand, or it will buckle. Now let's move on to heat, phase changes, and calorimetry. Heat is energy in transit from one body to another as a result of a temperature difference. Heat flows from hotter objects to colder ones. The heat Q required to cause a temperature change delta T in a material with mass m is given by Q equals m times C times delta T, where C is the specific heat of the material. The specific heat tells us how much heat is needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius. When a material changes phase, like from solid to liquid or liquid to gas, its temperature remains constant while it absorbs or releases heat. The heat required for a phase change is Q equals m times L, where L is the latent heat of fusion for melting/freezing or vaporization for boiling/condensing. Calorimetry is the measurement of heat exchanges. A fundamental principle in calorimetry is the conservation of energy. In an isolated system, the algebraic sum of heat gained by some parts and heat lost by other parts must equal 0. We can write this as sum of Q equals 0. For example, if a hot metal object is placed in cold water, the heat lost by the metal equals the heat gained by the water, assuming no heat is lost to the surroundings. Finally, let's discuss heat transfer mechanisms: conduction, convection, and radiation. Conduction is the transfer of heat through a material without bulk motion of the material itself. It occurs when faster-moving molecules, higher temperature, collide with slower ones, lower temperature, transferring energy. the heat current H, or the rate of heat flow through conduction, is given by Fourier's law. H equals K times A times the temperature difference divided by L, where K is the thermal conductivity, A is the cross-sectional area, and L is the length of the heat flow path. Convection is heat transfer through the movement of fluids, either liquids or gases. As a fluid is heated, it becomes less dense and rises, while cooler, denser fluid sinks. This creates a current that transfers heat. Examples of convection include boiling water, home heating systems, and atmospheric weather patterns. Radiation is energy transfer through electromagnetic waves. Unlike conduction and convection, radiation requires no medium and can occur in vacuum. All objects emit thermal radiation based on their temperature. The radiation heat current H is given by the Stefan-Boltzmann law. H equals A times epsilon times sigma times T raised to the fourth power, where A is the area, epsilon is the emissivity of the surface between 0 and 1, sigma is the Stefan-Boltzmann constant, and T is the absolute temperature in Kelvin. When an object at temperature T radiates to surroundings at temperature T0, the net radiation heat current is H net equals A times epsilon times sigma times T to the fourth power minus T0 to the fourth power. Let's summarize what we've learned in this thermal physics lesson. First, we explored temperature scales and thermal equilibrium, understanding how Celsius, Fahrenheit, and Kelvin relate to each other. Next, we studied thermal expansion and thermal stress, learning how materials change dimension with temperature. Then, we examined heat transfer, phase changes, and calorimetry, including how heat causes temperature changes or phase changes. Finally, we covered the three mechanisms of heat transfer: conduction through solids, convection through fluid movement, and radiation through electromagnetic waves. Understanding these thermal physics concepts is crucial for engineering applications, building design, meteorology, and even cooking. Thanks for watching, and I hope this has helped clarify these important principles.